Hello students, this is part 3 of chapter 2, and what we go into in this video is bonding, covalent and ionic bonding, and I want you to pay particular attention to what holds the atoms together in a covalent compound and what is the attractive force between ions in an ionic compound. Later, after that, we distinguish between the two so you can tell the difference. We last talked about what the atom looks like. It has a nucleus and electrons layered around it. So I want to give you a little bit of a better picture. In the first layer, there is what we call the first shell, and you could fit 2 electrons in it. Once 2 electrons are in it, that's filled up, and you need to go to the next level. The second shell or second level, n equals 2, can hold 8 electrons. Once that's filled up, you go to the next. So as you build on more and more electrons, you get bigger and bigger. But also what's more important is the ones that are closer to the nucleus, they're held more tightly because plus attracts minus. They're harder to pull away from the atom. The outer ones, though, are further away, not held as tight. So those can be used for bonding or reactivity or forming ions. So what we're going to be talking about and focusing on are the outer electrons, also called valence electrons. Each column, 1A, 2A, etc., each column has elements grouped by similar outer electrons. Group 1A has 1 outer electron. That's hydrogen, lithium, sodium, etc. Group 2A has 2 outer electrons, 3A, 3. So what's nice to know is the group number is the number of outer electrons, the halogen 7. So all of these dots that I'm showing represent a single electron, and they're arranged around 4 sides of the atom symbol. You can have a max of 8, 2 on each of the 4 sides. So elements want to get to 8. So for example, group 7 could add 1 or share 1. Group 1 will give up 1. Hydrogen special, it's fine having 2, and it can share or gain 1. You guys will be watching this video. So it's a fun video on how atoms bond, and it gives a big and more constricted view. Chemical bonds are forces that hold atoms together. So the main driving force for atoms doing this is they want to get the same electron configuration as the nearest noble gas. Getting to that 8 electrons around it, we call that an octet. So the forces that actually hold atoms together, at the end of the day, it'll be positive charge attracting a negative charge, and we'll get into those details. The types of chemical bonds we'll focus on are covalent and ionic. Covalent electrons are shared. Ionic electrons are transferred to form positive or negative ions. And metallic is something we don't focus on in this class, but it's bonding between metals, like in a piece of gold. Basically, you have the core inner electrons, and there's a sea of electrons floating through the different nuclei, sharing those electrons throughout the other nuclei present. Okay, covalent bonds. The key here is they're maximizing attractive force between unlike charges and minimizing repulsions between like charges. So this is the key thing you need to come away with. A proton is positively charged and an electron is negative. Those will actually feel an attractive force and be pulled together when they see each other. So these two proton, electron, this is a hydrogen atom. These 2 hydrogen atoms aren't interacting. When they get close though, the electron and proton feel each other and they literally get pulled together. There is a real force on pulling them together. You could think of it like 2 magnets, if you felt that before, and shoop, they get closer together. The magnet against the refrigerator door, that gets stuck there. That's that type of force that I'm talking about. This is the glue that holds atoms together. So you have this perfect distance, in our case, the hydrogen bond distance, where the electrons are attracted to the protons of both, but you're minimizing the repulsion between like charges, same charges such as electron-electron or proton-proton. And I'm showing this as two dots or two electrons being shared. So each hydrogen views that they each have two. They have fulfilled their duet. Hydrogen occurs as a molecule. It likes to exist this way, as does nitrogen, oxygen, and all the halogens. They like to exist as diatomics. There are a couple others. Phosphorus, if you take phosphorus from nature, it's not just a P by itself. It's not P2, it's P4. It's tetratomic, and 4 phosphorus are bound together. Sulfur and selenium are actually octatomic molecules. I just want to show a quick photo of octasulfur. It's gorgeous. It's a yellow solid, but when it's burned, it melts into a blood red liquid and emits a blue light when it burns. I mentioned that atoms want to become like a noble gas. If a nonmetal binds another nonmetal, you get these covalent interactions that I already talked about to form a covalent bond. But if you have a metal interacting with a nonmetal, what you want to do is generally what you'll see is ions will form. Group 1A and 2A tend to lose their outer electrons to become like the previous noble gas, sodium giving up 1 to become Na plus cation, and then chlorine gaining 1. Now it has an extra electron, it'll have a negative charge, and we call that an anion. So if I take sodium, 11 protons, 11 electrons, that's neutral, right? And I remove one of the electrons, I get Na plus, because now I have one more proton, one more plus charge, so it gets a 1 plus. Group 2s will remove 2, so you'll get a 2 plus. And I just put an electron here on the product side. This is like an equation. This is what you start with, this is what you go to. Na plus, and then you had kicked out an electron. It's actually given to chlorine, but I like to show it here as a product lost. And then a chlorine will gain an electron to give Cl minus an anion, a negative ion. Here's a way to remember it. Think of a lost cat. This is for the cations. A lost cat, if you lost electrons, you're a cation. And I'm positive. I have a positive charge. Okay. Ionic compounds, the simplest one is, we call that binary, bi for 2, just simple from 2 elements, like sodium chloride, Na plus, Cl minus. If we take a view close and just look at this, you see they're alternating arrays of cation and anion. The reason is if you had 2 pluses next to each other or 2 minuses, boom, they just separate. And so it's this nice alternating array. Look, it's a solid. Do you remember that constricted view where we were looking at solids, liquids, and gases? The atoms are in a nice, neat, orderly array. They're not flying around like ping pong balls. In ionic compounds, those are composed of ions. The key here is in this bond, this isn't a covalent bond. They're not sharing. So the protons aren't attracted to the electrons of another guy. You actually are the positive and negative charge. So the Na plus is a positive charge, the Cl minus is a negative. So you don't see it, nothing's being shared, but the plus is attracted to the minus. That's your ionic bond in between those. We call that an electrostatic attraction. So Na plus gives up an electron to Cl to give your ions. There's a great video here of that. And if we look at it based on that atomic model view I showed you, the outermost electron of sodium, that's the most reactive, easiest to pluck off away from the nucleus. These are held more tight. You don't want to, it'll take way too much energy to get these guys out. But this one hanging off at the edge, I'm going to pick that off and I'm going to give it to chlorine here. I'm going to form my ionic bond. You don't see anything, but this is a plus, a big minus charge. They're going to find each other and swoop and get close. It's a real force. Think of that magnet up against that refrigerator. So I already showed this. I won't do that again. How do you predict ions? So again, they want to become like the nearest noble gas. The main groups are easy to do. The middle elements are trickier because sometimes you could form more than one. Like iron can form, iron 2+ or 3+. But zinc and a few others like to only form one, like zinc 2+. I'm going to give you better details. The metals want to become cations. So this is a periodic table rolled on itself. This is actually your typical left side, group 1A and 2A, 3A. Here is the noble gas row. Here are the halogens. I'm just rolling it on itself to show that group 1A just needs to remove or lose one electron to become like the previous noble gas. Group 2 will remove 2, 1, 2 to get to the previous noble gas. Group 3, like aluminum, will remove 3. The halogens, all they need to do is gain 1 to be happy. Group 6A, and remember, if you're in the same column, you're going to behave the same. So sulfide will form, oxide will form by gaining 2 electrons. N, P, and nitrogen, phosphorus, arsenic, they'll gain 3 to become like the next noble gas. That's how you guys are going to predict what ions form. So always know, and write on your own periodic table, group 1 always will be +1 cations. Group 2, 2+ cations, and we do write the number and then the charge after that. Group 7, or the halogens, 1-, 6A, 2-, and then 5A, 3-. Just commit that, write that down, commit it to memory, always for those columns. Special ones I do need you to know are silver, zinc, and aluminum. These are ones that will only form these charges. You can remember this as they're in a diagonal. Silver is a +1, 2, 3. So it goes 1, 2, 3 in a diagonal. The rest you don't know, and I won't expect you to predict it unless you have it given in a formula or you have additional information. The reason is cobalt can form a couple of them, and these aren't all of them. There may be more ions. Ruthenium can form more than these two. These are just examples. So these you can't necessarily predict, but the ones in yellow are always those numbers. The way that you call the name of the ion is you just use the metal name for the metal, like calcium 2+ ion or rubidium plus. Over here, though, you take the root of the name and you add IDE, like nitride, oxide, fluoride. Okay, and then these are also metal names. So I already showed you ionic compounds, cation and anion. We don't call these molecules, we actually call these formula units. I'm not too concerned about that. What else? The main thing is, remember, it's an electrostatic attraction. One of the last little bits is talking about polyatomic ions. So sometimes you can have molecules that are actually ions because they have more or less electrons than usual. So let's take a look. Nitrogen trioxide. That guy is neutral, so it's not an ion. It's made of 2 nonmetals, so it's a covalent compound. No net charge. But this guy, that negative sign right there tells me this is an ion. So when you're not sure if you have a covalent neutral compound or an ion, look at the charge. Look what if you're paired with something. Like if I had lithium nitrate, then the nitrate is an ion, net charge of -1. These are covalently bonded units with the charge, and they act as a unit. So if you react with these guys, you don't break up N's and O's. It always stays NO3, but it's a minus charge. These are some examples. The only polyatomic cations to be familiar with are ammonium and hydronium, which is a H on an ammonia molecule and an H+ and an H+ on a water molecule. There are a variety of ions. You can just pause and familiarize yourself with these. I also have some that I need you to memorize. That's these. And just notice there are different charges. These are all polyatomics. The ammonium is the one cation you do need to commit to memory. Okay, we'll do 2 concept checks. So answer these, go ahead and pause, and I'll go over them. So you're going to predict the ions and label as cation or anion. So the first one is S2 minus, that's sulfide anion. An ion from calcium is Ca2 plus, that's a cation. Iron losing 3 electrons, Fe3 plus. It lost electrons, so it's a cation, and it's positive, like a kitty cat. The next is figuring out, are these covalent or ionic compounds? So CO is here in the nonmetal side, that's covalent. K and Cl, you have a metal and a nonmetal, so that is ionic. Another metal, aluminum, it's to the left of the staircase of semimetals, so aluminum plus chlorine, you have an ionic compound, that's a metal plus a nonmetal. NO3 neutral, 2 nonmetals, that's covalent. Sodium nitrate here, that's ionic because you have an Na plus and an NO3 minus. How did I know? Because I can't have a neutral compound with a metal. This unit had to have been actually a total of a -1 charge to match and balance out the plus charge of the Na. And then zinc bromide, zinc is a fixed 2+ charge, always 2+. It'll pair with that bromine nonmetal and give you an ionic compound. Okay, I'm going to end here, and I will talk to you guys soon.